We have here four integrals, each of them defined for a certain range of parameters and by integrals which are improper, of the first or second kind, depending on the integral. And what we have to do is to prove that within the range of parameters that we're given, these integrals are convergent. Okay, let's begin with the first one here. And here what we have is an integral which you have a power of x and a power of 1 minus x, right? Both powers can be negative. That means that this function here can be singular at x equal to 0 and at x equal to 1. Actually, at both limits of integration. So this is a double improper integral of the second kind in both limits here. So what we have to do to analyze this integral is to separate it out into two different integrals and study them separately. So the first one is from 0 to 1/2 of x p 1 minus x q dx, and the second one is from 1/2 to 1 xp 1 minus x q dx. Okay, now this one here is only singular at 0 because at 1/2 there's no problem with this integrand here, so it is this bit here that may cause any trouble. About this one here, one thing we can do is to make a change of variable here, and then what we do is we transform this integral into the following, but let me just copy the first one, right? I'm going to copy this one, put it here. Okay, so this is equal to this, plus, and for this second integral here, I'm going to use the variable t, which is 1 minus x. Okay, so dt is minus dx. With this minus, we're going to reverse the limit of integrations. And the limits of integrations are, for this one, x is equal to 1, so t is equal to 0. So the lower limit is going to be 0. We're putting the upper in the lower because of this minus here, to compensate for this minus. And for the lower limit, we have what x equal to 1/2, so t is 1/2, so what we have is this. And finally, we have that this is t, so tq, and x is of course 1 minus t, so we have 1 minus t p dt, which is fine because what we have here is two integrals which are similar, and the only difference is the exponents of the variables, right? This function is well behaved at 0, so is this one. And here the only singular function is this, and the only singular function here is this. So whatever we can say about this for p and q, we say for this one for q and p, right? So let's focus on this one, and then we conclude for both. We have this argument here, right? And we have, because of the binomial theorem, we know that this is equal to 1 plus O1 when x goes to 0. Actually, the next term would be minus qx plus ox, but we're not going to really need this one. We just need to know this. Actually, the only thing we need to know is that when x is very close to 0, this function is close to 1. That's the only thing we need, which means that this function behaves perfectly well. So then this function here is equal to xp plus oxp when x goes to 0, right? Or in other words, this argument xp1 minus xq is equivalent to xp, just xp, when x goes to 0. So all we need to analyze is what happens with the integral from 0 to 1/2 of xp dx, sorry. Which, if we write like this, x2 minus p, then we can say something, because we know that this integral here converges if and only if minus p is smaller than 1. And if we multiply this by -1, what we have is p larger than -1. So that is the condition. It's actually the condition that we have here. And this is for this one, but for this one we have the same condition on q, so q has also to be larger than -1, and this is the other condition that we have there. So yes, for this region of parameters, this integral here is convergent, and actually we know more. We know that outside this region of parameter, this integral is divergent.